good morning and a good evening to Taiwan, Asian, and U.S. American participants. Welcome to Data Analytics Colloquium. Today, we are really excited to have our advisor and colloquium advisor, Dr. Chris Achen of Princeton University. And Dr. Achen is going to present a recent paper he co-authors with one of his students and Dr. Won-Ho Park of Seoul National University. And Dr. Park, however, is engaged in another event. So we will have Dr. Achen to do the solo presentation today. And allow me to have Dr. Peter Pan to get started with the introduction, please.
Okay, good morning, everyone, and good evening. So thank you for coming on board for today's deck presentation by Professor Chris Achen. And it's really an honor to have him back again. He is our advisor, actually for this, when we initiate this colloquium, and he's the one who supported us the most. And really appreciate that all his efforts and all his support of this initiative. So today he's going to talk about the topic about rescaling problem in nonlinear probability models. And so before we start, let me just briefly introduce you to about this deck, Data Analytic Colloquium. And this is started at this is the third year. It's the third year.
Yes.
So yeah, it's the third year, and well, we can call it the third season. So we are not a year-long program. Usually, we use the second half of the year, and then we convene people, and then we invite very well-known professors, scholars, and try to share this data analytic techniques or new ideas and really up-to-date data analytics methods to all the audience. So, and I'm really I really appreciate that all the speakers and the scholars who have supported this colloquium. And then I'm hoping that we can continue to work on this so we can share all this knowledge, or especially in this data analytics methods to all the audience, especially our students. And well, that's about it. And then I will have to turn this microphone to Dr. Chris Achen for today's presentation. Thank you.
Allow me to do some introduction first.
Sure.
Hello.
Carl, go ahead.
Sorry, and I think for those who may have attended our previous events, I think you may be familiar with Dr. Achen. For those who are first time attending to our event, and I want you to get to know more about Dr. Achen. Dr. Christopher Achen holds the Roger William Strauss Chair of Social Sciences at the Princeton University, and his primary interest public opinion, elections, and realities of democratic politics. And he is author of books, and including one of the really the bestseller rank at Democracy for Realists with Professor Larry Bartels, and that is the book, and the winner of the two international awards. Maybe today, that maybe there could be more, and it's really a really important book for those who are interested in American democracy and so public opinion. He's also the authors of multiple books and also plenty of articles. And one of the most notable achievement is his book on the Taiwan voter title, also the Taiwan voter, with Dr. T.Y. Wen of Illinois State University. This is one of the most important books and about the Taiwan elections, voting behavior. And I highly recommend you to take a look at that edited volume by Dr. Achen. Dr. Achen is a member of the American Academy of Arts and Sciences, and he received multiple fellowships And from the Center of Advanced Studies in Behavioral Sciences, the National Science Foundation, and the Princeton Center for Study of Democratic Politics. He's also the founding president of the Political Methodology Society and received the first ever Career Achievement Award from the Political Methodology section of the American Political Science Association. And he has served on several social science boards at National Science Foundation and also the chair of the National Council for Inter-University Consortium for Political and Social Research, acronym ICPSR. And he's he's not only prolific in his work in his publication, but he has a lot of students, and his students are populating the top departments, top university in the United States, Europe, and also in Asia, including one of his co-authors today, and Dr. Park. And he has so many students, I do not want to name all of them. And chances are you go to some of the top universities and you can ask Dr. Achen, they may know him or they may know his student too. I think without further ado, I think I'm taking too much time. Allow me to introduce Dr. Achen.
Thank you so much for that gracious welcome, Karl, and thanks to you too, as Peter, for hosting this. Can you hear me okay now in Taiwan?
Yes, thank you.
Sure.
Okay. As Karl said, I'm a big fan of Taiwan. I have been there many times, and I have very good friends there. And I'm a particular fan of the restaurants in Taiwan. So when my friends want me to come back, they say, we went out to this interesting new restaurant and we left an empty chair for you. And that always gets me to return. So it's an honor for me to be addressing colleagues in Taiwan, where so much good political science is being done. And I hope that what I talk about this evening will be of some value to those of you, particularly students who are starting out. Okay, let me try sharing my screen here. Can you see that? Has that come up?
Yes.
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 Okay,
Yes.
good. Okay, good. So this is joint work with, and relatively new. We presented the first version of this at the American Political Science Association meetings in Montreal about 6 weeks ago. And Dr. Park apologizes for not being here. As I mentioned earlier, he's a dean, and if you're a dean, you don't control your own life. So he's sorry not to. Okay. The paper that I want to present here is a little bit technical and a little bit complicated. And if you are listening to me and parts of it seem a little bit hard to follow, believe me, we had a lot of trouble with it ourselves. So there may be places today where I don't do a very good job of explaining. And all I can say is two things. First, the conclusion of the paper is very simple and very easy to understand. So just, be patient. And secondly, I'm happy to go back to anything that I didn't do a good job on in the presentation. So I want to start with the kind of thing that we want to complain about. This is Taiwan data, and the person doing this is comparing different probit models. So each of these columns is a different model. You can see that variables are in some of these models and have been omitted from others. Various variables are dropping in and out here. And what the person making the argument wants to do is to compare what happens to party identification. And in particular, the author wants to say these numbers are pretty much the same and they are comparable, and therefore these other variables aren't they don't change the effect of party identification. Now we have a simple message here. This is a mistake, doing it the way this person did it, and we want to criticize the way that the analysis was done. Probit coefficients cannot be compared across different specifications. When you drop variables in and out of a probit, they're no longer comparable. And that's also true for logit, multinomial probit, and a variety of other nonlinear probability models. We don't teach this, but we should. It's a fairly serious problem. So the example that I gave, the author was just wrong and not doing it correctly. Now you may be saying, who was that author? It's me. It's from the Taiwan Voter, actually, and work that was done only about 5 years ago. And just to put it simply, I did not understand this problem 5 years ago. And so, but many other people have done the same thing. And what we want to do, Dr. Park and I, is bring attention to this problem and suggest a better way of doing it so that the coefficients are comparable. That's what this talk is about. So what exactly is the problem? We're going to talk about a very simple case in this paper and in this presentation. So suppose that the true model is this: y star is equal to x plus z plus u. If a little more familiar version of this would be to have an intercept term, a coefficient on x, a coefficient on z. But what we're saying here is the intercept term is 0, the coefficient on x is 1, the coefficient on z is 1, and then this is a disturbance term. So we're going to consider the case in which x, z, and u are each independently distributed and standard normal variables. So they have a variance of 1, each of them. Now, what happens when we leave a variable out? So to go back to the example with which I began, the person doing that, me, started with a full model and then dropped some variables out, right? And so this again is the simplest case. We are only dropping out z here, and we're estimating what this looks like with just x and with z omitted. So z now, this is the truth here. So z in this specification gets dumped into the disturbance term. So this is the new disturbance. It includes the old disturbance plus z because we're not controlling for z. Here's the intercept, here's the slope. The RF subscript stands for reduced form. So this form is reduced from the truth because z has been omitted. So we're going to estimate this, and when this is true, and see what happens. Now, if this is a linear regression problem, there's no difficulty at all. We will get the coefficient of 1 here, which is the same as its coefficient here. Why will we get that? Because it's a well-known result in linear regression that if a variable z is uncorrelated with x, then you can drop z out and you'll still get the same answer. So those of you who've had a good regression course, they told you about that. And we do this all the time, right? We leave out variables that are just uncorrelated, and we know that doesn't bias anything. Now, what happens in the probit case? So this is the setup in which this underlying variable z star, which I showed you on the previous one. So this again is the truth. This now is the underlying utility in probit. And we observe a 1 if y star is greater than 0 and otherwise y equals 0. So those of you who've been exposed to probit analysis, this is just the standard case. So one way to write the probit model is to say the probability of getting a 1 is capital phi. This is the standard normal integral of this specification here, linear in A, B, and C. And if we ran that, we would get the right answer, which is that B is equal to 1. Well, what happens in probit when we drop Z out? We just saw in regression, X and Z are uncorrelated, even independent. We know in regression that causes no problem. You throw Z away, you still get the right answer. In probit, though, it turns out you don't. In this model, you get a probit coefficient of about 0.7, not the correct answer. So the probit, when you leave out a variable in probit, you get a completely different coefficient, even though nothing has changed about X, right? X is just as powerful as it was before, but its coefficient has been cut by more than a quarter. That's how probit works, and that's what we haven't been paying enough attention to. That dropping variables in and out doesn't leave other coefficients comparable. They can be bigger or smaller than your original model and still represent the same effect. And that's kind of disturbing. Why is that the case? Why are they doing this weird stuff? The answer is that in probit, the underlying variable y star is like a utility, right? It's like a cardinal utility in economics. And cardinal utilities have no scale. They're only unique up to a linear transformation. So you have to fix something in order to set the scale. And what we fix is the variance of the disturbance being equal to 1. That's how probit coefficients are determined. We set that variance equal to 1. So in this case, we start with this one. This is the true model. We set the variance of u equal to 1. That produces the correct coefficient for x. But look what happens when we do the reduced form. Now, w is not just u, it's u plus z, because we threw z away, right? We didn't use it. So u and z are both independent standard normal variables. So their variance is the sum of their variances. And the variance of the sum is the sum of the variances, and each of them has a variance of 1. So the variance is 2 now. So, but probit says to itself, well, I have to rescale the disturbance term so that it has a variance of 1. That's just how it works. So it, in effect, divides everything by the square root of 2. So W has a variance of 2, as we just saw. If you divide it by the square root of 2, then its variance, the variance of this whole term becomes 1, which is what probit wants. But now everything else has been altered also, right? So instead of having a coefficient of 1 on x, we now have a coefficient of 1 over the square root of 2. That's just what probit does. 1 over the square root of 2 is 0.7. It's that same number we've already seen. So this is why dropping variables in and out of probits changes the coefficients, even when nothing about that variable has changed. It's just as powerful as it was before, neither more nor less, but its coefficient is different. We simply don't pay enough attention to this. I don't know how else to say it. I didn't pay enough attention to it. I've taught this subject many years, and I should have been more alert, but I just wasn't. So what are the proposed fixes to this in the literature? They are 4. One of them is rescaling. So instead of setting the variance of u to 1, you set the variance of y star to 1. That's an old proposal due to Winship and Mari in a long time ago, 40 years ago. The second proposal is to use average marginal effects instead of raw coefficients. I'll say more about each of these in a minute. There's a technique from 10 years ago called the KHB method, named for the people who invented it, which has been popular, particularly in sociology. And then there's the linear probability model, which is just don't use probit or logit, just run a regression, right? So those are the four basic solutions. In the interest of time, I'll be a little bit brief on them, but I want to say just a little bit. So as I've already said about Y star standardization, we just, instead of this way of setting the utility scale, we use this utility scale instead. And the reason you want to do that is that the variance of u is not fixed, because the variance of the disturbance is not fixed, I should say, if you drop variables in and out. But the variance of this dependent variable is fixed. And so it's a way of solving the problem. And I say a little bit here about how to compute it, and I can say more about that in the question period if you're interested, but I'll skip over it for now. What this example shows is that if you rescale in this way, in the example that I showed you earlier, where the real coefficient is 1, but probit comes up with 0.7. If you rescale both probits in this way, you get the same coefficient on x for both of them. So it does what it's supposed to do. The second proposal is the average marginal effect. Now, this can look a little intimidating at first glance. It is the partial derivative of the probability that y is equal to 1 with respect to the explanatory variable. So you get something that looks like this when you do the calculus. Now this looks a little scary, but just remember that in the regression case, this partial derivative is just the regression coefficient. That's all. So this is the equivalent of a regression coefficient. It just, because it's nonlinear, it takes a little bit of extra work, but the idea of it is very simple. So what you do is you take this derivative, you average it over the distribution of the x's. Again, looks complicated, but in practice, you just take an average. And the Stata program has a command that you can use after a probit or a logit. That's just margins dy dx, and it computes these for you, so you don't have to mess with all of this stuff up here. KHB method is an almost mysterious one. What they do is, in the reduced form here, where you have only x, they add a variable e. And what is e? It's the residual from a regression, not a probit, just a regression of z on x. So you regress z on x, you put the residuals in to this thing, and you get a coefficient g, and then you just do probit as you would before. And it gets a different estimate of b than it would have gotten if e weren't in there. And the different estimate it gets is the correct answer. So again, in the original problem, where the real effect of x is 1, this procedure on average produces a coefficient of 1. So it's not 0.7. So it fixes the rescaling problem. This one's hard to understand intuitively, but they prove that it works, and we've done a lot of experiments with it. It does. Lastly, as I said earlier, we just run ordinary regression on these two. You know, it's misspecified. We know that. but the idea is, maybe it's not too bad. So I'm not going to show our results for it tonight. We've just done them in the last 10 days, and I don't have them written up yet and incorporated, but I will tell you how it comes out. So what we did in this paper is this: we computed each of these estimators, and we compared how well they do, and I'll explain what how well they do means in just a minute. And those estimators are these. The first one is naive probit. That is, you just ignore this whole problem and do what I did in that original example that I gave at the start. You ignore the problem. Secondly, the Y-scale estimator that I've talked about. Thirdly, the AME, the KHB, and the linear probability model. Now, what we do is simulations. And those simulations work in the following way. Each simulation draws a sample of 1,000 observations. We then run all 5 of these and write down and keep track of what answer they give in that case. These are random samples, so you don't get the same answer every time. And we do that 10,000 times. So the total number of individual observations here that are being drawn is 10 million. And we average how well each estimator does. So again, the basic setup here is this. This is what we're estimating. We're looking at the coefficient on this coefficient on X, where Z has been omitted. So Z is out here in the disturbance term. This is W. We're just regressing. We're just doing probits with one explanatory variable, and that's X. And the question is, what coefficient are we getting here? The correct answer on the regular model is 1. Some of these estimators put things on a different scale, but the idea is, do they give you the result that dropping out Z doesn't change anything? That's the truth, right? X and Z are uncorrelated. Dropping Z should make no difference to the effect of X. And in the naive case, it does. It screws it up. These other 4 techniques are designed to fix the problem and give you the same answer when X is included and when it's excluded, as it should give you the same answer. So that's what we're looking at. Now in these simulations, these 10,000 samples, we consider different cases in which the variable Z that you're leaving out is distributed normally, uniform, Bernoulli, that means dichotomous, or log normal. Log normal has a very long right tail. It's skewed to the right. And what we do is we see how well each of these 5 estimators does. Now, again, what does it mean to say that you're doing well or doing badly? The measure is this. We take the true value and we take the estimate produced by on any given run. We take the estimate and we subtract it from the truth and we square it. So why do we square it? We square it because you don't want the cases where you're too high to cancel the cases where you're too low. They're both a miss, right? So you square it so that all the misses are positive in sign, and that's a measure of how wrong you are. So we get a calculation like this for every sample. So again, 10,000 samples. We draw 10,000 samples. So there are 10,000 of these sigma i's. For each one of them, we look at this number. Now, we then average it, right? We take each of these 10,000 squared errors and we divide by, this should be 10,000, not 1,000. We divide by 10,000 to get the average error. and then, because this is a squared miss, we take a square root. And this is the average absolute miss. Now, how far wrong are you on average with the square root getting you back to the same scale as the coefficient itself? Then lastly, because these different corrections put things on a different scale, so if you standardize by y star, for example, all your numbers are smaller. You don't want to give credit for that. You want to have everything proportional to the true value. So what this whole thing, this scary looking thing is telling you is just how far wrong are you on average as a proportion of the truth, right? So if you get 0.04, for example, that means on average you're off by 4%. So it has a simple, relatively simple interpretation. Now, what are the true values? Well, for naive probit and the KBH estimator, the true value is 1. For Y-scale, you can use things you know to compute it, so that's straightforward. The true average marginal effects are more complicated. They require a convolution, and then it's average over the distribution of X. So it's this thing. It's a little ugly. We computed them analytically. One case it was too hard, and there are only approximations, but we did those as well. So this is what those true values look like for different values of S, which is the standard deviation. Now, how does this come out? I've got a lot of these, and I'm not going to go through them all, but I want to go through a couple of them to give you a feeling for it. So again, this is the case in which everything is normally distributed here, including Z, the excluded variable. It has a variance in this first column of 1/2. In this column, it has a variance of 1. And in this column, it has a variance of 3. How does the naive probit estimator do? And the answer is terrible, as you would expect. It's wrong by about 19% of the true value in the case when the variance of Z is 1/2. When the variance of Z is bigger, it gets worse. It's off by about half the value of the coefficient on average. So if the real coefficient is 2, then you're getting a number like 3 or 1 about half the time, and the other half of the time, so half the time worse than that and half the time better. But it's not good at all. By contrast here, the Y-scale and the AME give errors of about 4 or 5 percentage points in these cases, and about 7 here, and they're equivalently good. The KHB estimator, again, popular in sociology, is not terrible. It's off by about 7% when the AME is off by 4%, and so on. But it's simply not as good. So this is the case that works the best for the Y-scale. I will show you the log normal case, which is a little different. Here, naive probit has substantial errors. The good one is the AME. It's off by about 4%, and this here it's 4.5, here it's 5.5, and it's particularly when Z has a large variance, the AME is a lot better. It's almost twice as good as the KHB. This is an average error of 9%. And Y-scale just goes to pieces. It's off by about 1/4 in this case. So I have here all of and I should say that the linear probability model looks about like the Y-scale in our estimates. It's not terrible, but it's not as good as the AME. So we have all of these results for different distributions. Some of them are a little more like the first example. Some of them are a little more like this example, but they all look kind of like this. The AME is just consistently better, and that runs through all of these results. So just a quick look. That's the case where X and Z are both uniform with variance 1. And again, 4% error for the AME, 5 for the Y scale, and 7 for KHB. In this case, the linear probability model is about 5 also. So AME is just better. Now, these things are all more or less unbiased. So you get approximately the right answer with all of them. But they're just, except for naive probit, which is seriously biased. But the others are, they hover around the correct value, but some of them hover more closely around the correct value than others do, and it's the AME that does the best job over and over again. So these are all additional examples. So I'm glad to go through all of those details or ask questions about particular cases. But what I want to talk about in the remaining time I have here is just so what, right? So the big result here is something that that we have known, but haven't done a very good job of saying or paying attention to. And we certainly, people like me, have certainly not done a good job of teaching it. That is that if you have different numbers of variables in your probits, even when the sample is the same and everything else, then the coefficients are not comparable, and that's just something we need to pay more attention to. These 4 proposals for fixing it are those I've mentioned, and as I've said, AME is just better. Not only when X is normal in our simulations, not only when X is normally distributed, but when it's not. There's an earlier article from about a dozen years ago that looked at logit. It looked at a much smaller set of alternative estimators, but it found similar results, that the AME was the best. So it's not just probit, but logit as well, for which this is the right answer. So here's the main message from this talk. And when you report results from probit, logit, multinomial probit, you should use average marginal effects. That's the AMEs, not the raw coefficients, Those are just not, those don't do what you want them to do. They are not comparable. The AMEs are comparable, and they are what you want. In addition, average marginal effects have a simple interpretation. They're just the changes in the probabilities of the outcome. So I'll give you an example of that in a second. So people have often liked them because they did have a simple interpretation, but the idea has been, well, yeah, but the coefficients are the real thing, and you should be showing us those. That's wrong. That's wrong, right? It's the AMEs that are the thing that you really want to present. They're unaffected by the rescaling problem, and they're more efficient statistically than other fixes. Incidentally, you can do mediation analysis with AMEs also, and they avoid the errors that come from doing mediation analysis with probit when you use the raw coefficients. So I want to conclude by showing you an example. This is actually an example that we used in our talk to this group last year when we didn't understand all of this as well as we do now. This is a study of the 2016 presidential election, in which Donald Trump was elected, and this is the effect on abstention in that in that election. And it looks at the estimate you get from probit, from multinomial logit, and from multinomial probit on extension. I'm sorry, on abstention. These are average marginal effects. So let's just take the multinomial probit estimate of the effect of Republican partisanship. So it's right here. It's about minus 0.05. What does that mean in plain English? It means that if you are a firm Republican partisan, you're a strong Republican partisan, that will raise the probability that it reduces the probability that you will abstain by 5%. Put the other way, it raises the probability that you will vote by 5 percentage points. See how simple that is to say compared to a probit coefficient? Here are the effects of being a woman on abstention. These are negative, meaning that being a woman, all else equal, all this other stuff controlled, you are more likely to, you are less likely to abstain. In other words, you're more likely to vote. And again, that effect is about 5 percentage points. Here's the scale. These are proportions. So this is about minus 0.05, which is 5%, right? Other things have a much bigger effect. So being well educated here has an effect of almost minus 0.2, meaning that if you're at the top of the education scale, you have postgraduate education, you're about 20% more likely to vote. So it's quite easy to use AMEs to interpret your results, and they do so in a way that is very easy to convey, very easy to explain to people who are not specialists. And this is, and unlike what we've thought before, which was that, okay, I'll do it this kind of dumb way with the AMEs, even though the probit coefficients are the real thing. Exactly the opposite's true. These are the real thing. These are what you can trust. You can compare them across different specifications, and they're also easier to interpret. So this, as I said at the beginning, this paper has two parts, a kind of technical, difficult to understand part, but it has a very simple finding, and that is when you do this kind of thing, logit, probit, and their extensions, use average marginal effects. That works just much better. Okay, that's it.
Okay. All right. Thank you. Thank you, Dr. Achen. So any audience have any questions? You can just use the chat box and to type on your questions, or you can just turn on your microphone and then speak up. Either way. So I have like a couple of questions for you, Chris. And I'm not sure, just like you said, for the first part of your presentation is quite technical, and not everyone can just fully understand all the details of this the technical part. However, there's a question here. Let me just read it out for you. So this is about the significance part. What would be your evaluation on the practical significance of the error caused by the rescaling problem? I mean, I think this question is related to the debates about p-value, using the p-value. Or the statistical significance versus the practical significance. I'm not sure if this is related to you, because the question is, we want to know that the error caused by the, let's say, the wrong way. And then this is the fixed. So it's more, I would say it's more correct. Allow me to say that. So what about the this practical significance?
I think that that's an excellent question. I think, to be honest, that most of the time the rescaling problem doesn't make too much difference. So I have not gone back to the Taiwan voter and redone those calculations. T.Y. Wang and I wrote that chapter together, but that particular set of calculations I did. I have not redone them to see how much difference it makes. I don't think it would be too dramatic. So if you're reading work that was done 5, 10, 20 years ago with probit or logit, I don't think you have to just throw it away. I think most of the time it's the problem is, you know, it's real, but not horrendous. But there are exceptions, and so going forward, I think it's something we want to get rid of, where we don't have to worry about it. We don't have to worry about whether this is the one case in 10 where it really matters a lot. So let me be a little more specific about that. When a variable that you're taking out is a big, powerful variable, that makes the rescaling problem worse. If you're taking out little variables that don't make too much difference, maybe you're taking them out because they don't have much of a coefficient, that's going to make much less difference. So you know, I don't want to exaggerate this as a practical problem compared to getting the model right with the right variables. That's way more important. But I do think it, you know, bears paying attention to. On the significance problem, I'm not sure how closely related that is, but I wrote about this a long time ago. In general, we pay too much attention to significance levels and not enough attention to the sizes of effects and their substantive interpretation. So I'm very much on the side of, you know, you see people say, well, this variable is insignificant, so its effect is 0. That does not follow, right? We want to see the 95% confidence interval and see how big or small it might be under different samples. So I'm not sure those are the same problem, but they both matter.
Okay, thank you. I think we have audience, Anna Zisco. I hope that I read your name right. He has, there's a questions from Anna, and she said, Dr. Achen, how did you realize that your initial method was not as accurate as the second one, AMEs?
Well, people in Asia and people in Taiwan in particular believe in family. And I have a daughter who is a sociologist, and she is the one who alerted me to this problem. So the short answer to your question is my daughter helped me. I you know, I kind of knew all this. I mean, I taught for many years the way that probit standardizes coefficients and so on, but I just didn't see the consequence, and I'm not alone. So this has been a bigger issue in sociology than it has been in political science, and it's just starting to appear in political science in a few articles. But she was the one who said, "Daddy, you can't do it that way." So,
well, obviously, she's a big fan of you, so she knows all about your works, right?
She knows increasingly, yes. When she was younger, we just wanted to be father and daughter. We did not want to be colleagues. We didn't talk about work very much, but in recent years, yes, we have exchanged more work.
Okay, all right. And
was that clear?
Here's another question.
Yeah, was I clear?
Anna, is that clear? Yeah, she said.
Yes,
thank you.
yes, thank you very much.
You're welcome.
Okay. All right, and then here I have another question. All right, take the logistic regression as example. I'm not sure if this is the right question. We use odds ratio instead of the coefficient directly to interpret the effects of independent variables on dependent variables.
Yes.
So, so the odds ratio and coefficient. So maybe this is the 101 question. So can you explain a little bit about the odds ratio, use odds ratio to interpret the effects, and what you just presented about using the coefficient, the argument about coefficient. So
Yes.
Can you tell us a little bit about this one?
Yes, I sure can. Yeah, as the question said, in logit analysis we use odds ratios, and coefficients in logit analysis, the coefficients are the log of the odds ratio. So they are a monotonic transformation of the odds ratios. And that's of course quite different from probit. However, both the logit coefficients and that is to say the log of the odds ratios and the odds ratios are both subject to the same problem that I mentioned at the beginning with probit. They are not comparable across different specifications. So it's exactly the same problem. And you don't get away from it by using logit or odds ratios. You have to use AMEs in logit analysis also in order to avoid the non-comparability.
Okay. So these fix either AME or the other three fix that you just presented. Do you think this is now the mainstream on the textbook, or no, not yet? So people are still using the traditional way to do this.
Yeah, it's still very much the case that most people are doing exactly what I did in that example that I began with. We hope nobody who has thought about it. It's not controversial among people who have thought about the problem because it's so clear that there's a real problem. But most of us haven't thought about it, and the reason we haven't thought about it, as I said, is that we don't teach this, and we should. One thing that Wan Ho and I want to do is in the next 2 or 3 weeks, get the linear probability model part into the paper and then send it off. And we think we're going to start with a sociological journal because they're more interested in the problem, and we hope that it will leak back into political science eventually. But some things I've written, they're controversial. Other people have a different opinion. Very smart people disagree with me, and those controversies are going to continue. This is one in which there's no disagreement among the people who've studied the problem. They all know they all know you have to do something. There isn't yet agreement on which of the fixes you should use, but there is agreement that you should use something, and any of the fixes is a lot better than doing nothing.
Right. This alarms me because I teach the quantitative methods too, and then when I come to this topic or this model, I never used this before, so this kind of alarming, and I have to change the way I teach my students. Then, I have to bring this into my classes.
Well, it was just
but,
as
in a way, I feel comforted that Chris, you've been making this mistake for so long, and then what about me? So I'm not worried about that. But thank you for showing this, and so I can just incorporate this thing into my teaching materials. Yeah.
That's just what I was going to say. You should not feel bad because I've been doing it wrong many more years than you have. So.
Yes, you did. That's true. All right. So any other questions that you want to raise to Dr. Achen? All right, and like you said, that this is quite well, although it's very technical, but the takeaway is quite simple. Uh, Whenever we come to this non-probability models, and then we have to use a different way to think about or to get the answer by using all these fixes. So the paper has been out, right?
Yeah, we just presented it at APSA, so it's at
Okay.
that conference in the middle of September. So it's deposited there. Anybody can call it up who wants to. And as I say, we'll have a revised version here in a couple of weeks that includes the results from the linear probability model.
Okay.
Anybody who wants a copy, of course, we're very glad to send it.
Okay.
My email address, I'll put it in the chat so you can see it. It's
Yes.
just
It's
Achen.
on the website. Yeah.
Yeah, it's just Achen at Princeton.edu. So
Yes.
it's very easy, and I'd be delighted to send it to anybody who wants it and answer any questions that you might have about a project that you're working on.
Okay. All right. And a related question, or just it's about this slide that on screen. Here's the example, and I'm just thinking that if you could compare the fix, the size of the fix that you have. Now this is the AME, right?
Yes.
This slide, it shows the
Yes.
AME. And then
Yes.
what's the difference? It's like the theta. I forgot the equation that you presented. It's the difference between using the traditional way or the wrong way and using the AME. So if you compare this, it will make this. This picture more complicated, but somehow you can, if it's possible, that we can, try to estimate or have a better look of how wrong it was, and then how right it is, and then see what I'm saying here to make a comparison. Maybe it's easier for the audience to catch the idea visually. Yeah, just a thought. I don't know. Yeah.
Yeah, that's a good suggestion, Peter. I think that this particular paper is directed toward the KHB estimator because that has been the most popular in sociology. And so
Okay.
a big focus of this paper is to say that the KHB estimator is a really smart, clever idea, not intuitive at all. But actually the AMEs work a little better. So that's our focus. But the broader message is the one that you just mentioned, and that's to show the problem in actual practice. And one possibility we're considering is that we want to write a paper more for political science that uses real data instead of simulations. And if we do that, then I think doing what you just said would be a really good idea. The problem with real data is you only get one sample instead of 10,000. And so you think, well, okay, it came out that way on this one example, but what else, how else could it have happened? But I do think we need to bring this to the attention of political scientists, and that
True. Yes.
there's work to do that.
All right. Okay. Thank you so much. And any other questions or comments for Dr. Achen? Okay, I think it's quiet today, and we have a relatively shorter presentation and a colloquium today. However, I did learn a lot because I didn't know about this before today. So I think I want to personally thank Dr. Achen for bringing this to us, bring this to our attention. So in the future, hopefully that whenever we use this kind of model or the extended model, and then we have to use the correct way, all right, to get the answer right. I think this is very important, very important. All right, so one last call. Any questions? So what time is it now, Chris?
It's 11 p.m. and I
11 p.m. Okay.
11
All right.
and I have a dissertation defense that I'm chairing at 10 tomorrow morning. So
Tomorrow morning.
yes.
All right, that's a good idea.
So,
that maybe we could just stop right here, right?
I'll go home. Carl is reminding us that about the announcement of the next one by Jim
Yes.
Granato, who's my good friend. And maybe you want to announce that too.
Yes. Let me just the next one. Let me just make this announcement. So Dr. Granado and Dr. Wang, and they're going to present the topic, so empirical implication of theoretical models in political science. So this is about another perspective to look at this how we do the theoretical models in the field of political science. I think that would be very interesting. And the date is November 3rd in United States evening. So in Taiwan, and November 4th. So please do come back and join us. I think this would be a very interesting topic to learn. And then I believe this will be a wonderful presentation too. So stay tuned and do come back. And thank you all for joining us today. And we hope to see you all very, very soon. Okay. Thank you, Dr. Achen, and for your time and effort and very insightful presentation. Thank you.
Thank you.
So good night, and everybody.
Thank you all very much too, and my very best wishes to the students in Taiwan for your your work and your future.
Thank you very much. Okay, good night.
Good night.
Bye. Yeah.